Hi everyone and welcome to today's webinar. This is a free educational webinar on dispatch and control systems in the HOMER Energy software. I'm Marilyn Walker, Chief Operating Officer here at HOMER Energy, and I'm excited to be here with you today and really appreciate you showing up. Our plan and our hope is to make these educational webinars monthly so that we keep you up to date on what's happening with HOMER and how to make the best use of HOMER software and also the other services that we offer here at HOMER Energy. So I have two HOMER experts with me here today, Dr. Peter Lilienthal, our CEO, and also the original creator of the HOMER software at the National Renewable Energy Laboratory, and Steffi Klawiter, our product manager. Arbi Madhavan is also here with us. She'll be watching for your questions and in some cases answering them in real time during the webinar. A little background on HOMER before we begin. It's an acronym for Hybrid Optimization of Multiple Energy Resources. We now have two different products, both focused on techno-economic optimizations of multiple energy systems, which is to say, they're both focused on helping you design the most cost-effective hybrid system that will meet your electrical needs. The HOMER approach includes three different processes nested together. At its core, HOMER has a simulation engine. It simulates the operation of an electric power system for 1 year, hour by hour, or minute by minute. And at each time step, HOMER looks for the most cost-effective way to meet the electric load based on the set of constraints that the user has defined. Simulation tells you how one system operates, and then the optimization step will simulate hundreds of different systems to find the least cost system. So we're optimizing for cost in two different ways. And then HOMER also has an option to do sensitivity analysis, which allows you to look at the impact changes and variables you don't have control over, such as fuel price or wind speed, have on your system design and system costs. Using HOMER to design and optimize your microgrid or distributed hybrid energy system has three main steps. First, you provide information on economics such as the interest rate, along with your energy demand profiles, your location, which tells us the renewable resources, i.e. solar radiation, wind speed, the types of equipment you might want to consider, shown here as system components. HOMER then steps through the three nested processes I talked about in the last slide: simulation, optimization, and sensitivity, and then it provides detailed results not only on the economics of the system, but also on exactly what's going on literally in every hour if that's what you need to know. Using HOMER, Today we're focusing in on dispatch, which is how the microgrid controller makes decisions on which components will serve the load when. Dispatch strategy is one of the choices you make when you set up your HOMER modeling run in that left step in that last slide, and it's one where knowing what to use when requires some real expertise. HOMER is the only microgrid modeling software tool that offers you 6 different dispatch choices right out of the box and also lets you model your own system. So today we're going to learn about what those choices are and why we have so many choices in the product and how to know which one to use. I mentioned earlier that we now have 2 different products. HOMER Pro is our flagship product. It's powerful and versatile, really available to work with almost any kind of microgrid. And then earlier this year, we introduced HOMER Grid, which was designed explicitly for behind-the-meter systems in grid-connected markets, where demand charge reduction, time of use rates, maximizing self-consumption, incentives, resiliency, or some combination of these are what matters most. So now I'll turn the controls over to Peter Lilienthal, the HOMER Energy CEO.
Well, thank you, Marilyn. And let me get my screen up on the webinar here. So hopefully you all...
No. You got it now.
Right. So hopefully you all see a nice big blue screen that says Homer's dispatch algorithms. So one way to think about it is to think about what market you're operating in. So Homer, as Marilyn implied, is used in a lot of different ways for a lot of different kinds of system and a lot of different markets. And so the original market was the off-grid, and we have 4 dispatch strategies for these sort of smaller off-grid systems. And then we decided that larger off-grid systems, what we often call island power systems or diesel-powered utilities, where you have multiple generators, needed a different dispatch strategy. So that's the generator order one. And then grid-connected microgrids are different as well. And we created a HOMER grid for that. So that's one way to sort of get your head around, since we have so many different dispatch strategies. So let me start with the off-grid systems. The original 2 dispatch strategies were load following and cycle charging. And the difference is pretty straightforward. In load following, you never charge the battery with the generator. The battery is just for absorbing renewable power. In cycle charging, whenever you need to use the generator, you might as well charge the battery at least as much as possible, limited by the size of the generator and the ability of the batteries to absorb charge. But then you want to stop charging at a set point that's one of the inputs in HOMER. So that's what we call a set point state of charge. We have a third strategy, the combined strategy, that intelligently switches between those 2. But let me talk about those 2 in a little more detail, because it does affect the results. So with load following, you do have less battery throughput. So in that sense, it's easier on the batteries. That leaves headroom for the renewables, so you can absorb more of the renewable power. It does tend to lead to more generator runtime and more start-stop cycles for the generators. So in that sense, it's a little harder on the generators. And it tends to be more appropriate for high renewable penetration systems, although that's a generalization that's not always true. So that's why you have to run the model, actually. Cycle charging, on the other hand, maintains a higher average state of charge on the battery, so that's better in that sense for the battery. It does tend to end up using more fuel, both because you can't always absorb all the renewable power, so you're not, so that's made up by the diesel, and also because you do have some additional round trip losses through the battery. When I talk about throughput, I mean the energy that's coming, the round trip energy going in and out of the battery. So the cycle charging does end up with more battery throughput, somewhat shorter battery life, tends to be more appropriate for lower systems with lower renewable penetration. Again, those are generalizations, and you really need to test that for your particular system. For smaller off-grid systems, my preference is to use the combined strategy because it's simple. You only need one, so it runs faster. It's never a bad choice. So especially for the initial runs, it's a good choice. And when I say intelligently switches, I mean when the net load, the load minus the renewables, is low, you cycle charge instead of running the diesel or generator at a low load. But when the net load is high, then it load follows. So that tends to work pretty well most of the time, and it's a good starting point. So that works well for your smaller systems with a single generator, maybe 2 generators. But if you have a lot of generators, those dispatch strategies tend to run really slowly because every hour it's doing a little tournament of all possible combinations. And so what we created was another dispatch strategy we call generator order. Some people might call it merit order for systems with many generators, because we do a lot of analysis for islands, utilities that have 10 or 12 generators. And then the as a user, you prescribe the order at which you use different generators. And we find this to be more consistent with the way utilities actually operate, where they do have a defined merit order. And so so I've defined it here, the very sort of simple system where there's a 100 kilowatt generator, a 200 kilowatt generator, and a 400 kilowatt generator. And if Homer can meet the load with none of, with diesel off, it'll do that. Then, assuming that isn't enough to meet the load, it works its way down this list. So first it'll try the 100 kilowatt generator. Can that meet the load? No. Then it'll choose the 200, the way I've got the check marks checked here. Then it goes to 200. Then it goes to 100 and 200, or 300 kilowatts total, and works its way down the list until it can meet the load. And you can define this merit order any way you want to be consistent with the way you operate your system. So this runs much faster and is preferable if you have many generators. It's important to talk about operating reserve, because or what utilities usually call spinning reserve. We like the term operating reserve better because we work with batteries so much and they don't actually spin. But it's the same concept. It's additional capacity available to meet the load on top of what the load actually is. And so there's two main purposes for the operating reserve. Contingencies are one of them. So most utilities have sort of an N-1 criteria. If a generator fails, there's enough online capacity to pick up the load so the system doesn't crash. But also for a simulation model like HOMER, which operates with time steps, it also is a way to cover variability within the time step. If you're using 1 minute time steps, you might not need quite as much operating reserve in HOMER as if you're using 1 hour time steps. And so I've got a screenshot down there just showing the inputs. So one of the inputs there says operating reserve as a percentage of the annual peak load, which is a constant. So if you always want, say, 200 kilowatts of operating reserve, turn that into a percentage of your peak load, that's the input. The first one, load and current time step, is a way to have the operating reserve change dynamically. So you might want more operating reserve when the load is high and less when it's low. But it's important also to think about the impact of your renewable power, your variable renewable power. So you might want more operating reserve as a function of what's happening with the solar and wind. So if you want to be super conservative, you put 100% there, and that means you could lose the renewable power instantaneously and you'd still have enough operating capacity to meet the load. That's very conservative. Typically if cloud passes over your panels, you might lose 70% quite quickly. So that's a number that you need a little experience with to determine, and one of the reasons we allow you to do sensitivity analysis on it. You might start conservatively and progressively become less conservative. And then my final point here is just something that confuses people sometimes in HOMER, because we have two output parameters, capacity shortage and unmet load. So because we require more operating capacity than load for this operating reserve, it's possible for HOMER to say, well, you've got enough capacity to meet your load, but you're not meeting your operating reserve. And so that would show up as a capacity shortage, but not unmet load. And so that's why frequently there'll be more capacity shortage than unmet load. And I always end up explaining that to people, so I thought I'd mention it. So now I'm going to turn it over to Steffi to talk about our predictive dispatch strategy and our grid-connected strategies.
So Peter mentioned he was talking exclusively about for the dispatch strategies which are in HOMER Pro. That was cycle charging, load following, combined dispatch, and generator order. And I'm going to talk about HOMER Predictive, which is in that final column there, before turning over to HOMER Grid's dispatch strategy. So about HOMER Predictive, here HOMER Predictive dispatches batteries most intelligently using a 48-hour look-ahead period. And so with HOMER Predictive, we're actually addressing maybe a shortcoming of other dispatch strategies which have no foresight capabilities. So in the other dispatch strategies, the operational decisions are made without any knowledge or forecasting of the future. And with the technology that's out there today getting better and better, you have more accurate solar forecasting and load prediction. So HOMER Predictive mimics these smart controller technologies. And in this example here, this is a cycle charging example. The graph on the left shows the electrical demand in the light blue and the solar production in yellow. So the generator is turned on, that's the red, in the morning and in the evening, and the battery is in the light green. What cycle charging does is that it keeps, the battery is actually at 100% state of charge going into what's going to be a very sunny day. And so because it's at 100% state of charge, it can't absorb very much of the excess energy, any of the excess energy which the PV is producing. So actually what HOMER Predictive offers is a solution for that. And HOMER Predictive knows that it's going to be a very sunny day and the PV production is going to exceed the electrical load demand. And so it keeps the battery state of charge as low as possible going into that day so that it can maximize the amount of PV output which it captures. So with that, I've covered all the dispatch strategies which are in HOMER Pro, and I'll just mention that there's all this flexibility and there's even more than this because you can create your own dispatch strategy or use the controller API, which I'll come back to later. Regarding the grid-connected hybrid systems or microgrids, that's why we created HOMER Pro, or HOMER Grid, thank you. And main value streams for HOMER Grid include peak shaving or demand charge reduction, energy or price arbitrage. And with this, I mean a very broad definition of arbitrage here, where this is where the battery is charging when the price is low and discharging when the price is high. So it could sell back to the grid if that's the most economic choice, but HOMER Grid will consider whether serving the electric load from the battery bank to avoid energy purchases at a high price can provide perhaps more value than selling back to the grid. And self-consumption is the third value stream. So a battery which may complement perhaps an oversized PV system will help maximize the self-consumption. So we'll go into these value streams kind of one at a time, talking about demand charge reduction. So for systems that are subject to a demand charge, HOMER Grid tries to use the battery or the generator, depending on your model, to reduce their demand charges. And so for each month, it's choosing a demand limit and seeing the demand limit is a maximum allowable power level in kilowatts, which you can pull from the grid at any moment. So it's an artificial limit, doesn't have any relationship to the hardware capacity. It's kind of a goal that the dispatch is trying to meet. And if the demand limit is too low, maybe we won't be able to supply the load in an economic way, and we should choose a higher demand limit. Or if the demand limit is too high, maybe we didn't use our batteries as much as we could have to reduce the demand charge further and save money. So HOMER Grid tries different demand limits for each month until it finds one that minimizes the operating costs for that month. So in this example, there's a PV battery and grid system, and there's more PV available in the summer reliably, which is why you can actually buy less during the summer. There is the option to even run with 2 demand limits per month, and since some utility tariffs include time of use demand rates, which only apply to maybe weekdays or certain times of the day, HOMER Grid can add a second demand limit, which coincides with these on-peak times, and it might save money when you reduce the demand even lower during that high demand peak, on-peak time. So that's how HOMER Grid's peak shaving algorithm really extracts extra value by driving the demand limit lower during the times of days when the demand charge applies. And that, yeah, this is how you can see where the black line drops down is during the on-peak times to reduce the demand during that time period. Regarding the second value stream, arbitrage, this can come into play when there's a large difference between the on-peak and off-peak times for the energy prices. HOMER Grid uses kind of price arbitrage, so it will serve the electrical load from the battery bank to avoid energy purchases during that high peak time. So in the plots here, we have in pink the electricity price, and the difference between the on-peak and off-peak times is about 12 cents, which you can see in actually both of the plots here. And with a battery, we could actually save money by using the batteries instead of buying during that high on-peak time. So you can see it's doing different things depending on the price. During the on-peak time, there's actually no grid purchases with your hybrid system. And then once it's in that shoulder period, the grid purchases generally follow the load, not exactly because it's balancing everything else. And during the off-peak times, the bottom there, the battery is charged because it's a very cost-effective way. To get to the third value stream for HOMER Grid, that's maximizing self-consumption. And the main point here is just that going into the weekend, this is a commercial facility, so it's the load during the weekend is much less during the weekday, but the PV is producing the same. So there's consistently excess PV on the weekend. And in this example, the peak shaving algorithm allows the battery to discharge ahead of these excess PV or excess energy times. So it's maximizing the self-consumption instead of having to sell excess energy. So you can see going into the morning of March 3rd there, we have the minimum state of charge, and the system doesn't buy any electricity overnight on March 3rd, and allows the battery to deplete as much as possible before March 4th when there's also excess. So with that, we've covered the 6 main different dispatch strategies which are available in the HOMER products and their various features. Depending on the markets or the technologies which you're interested in, HOMER has the right product and dispatch strategy for you. And lastly, I mentioned that you can further customize this with MATLAB Link and Controller API, but that is another topic for another day. So please join us next time for RB, who's on the line now, will be leading the webinars regarding MATLAB and Controller API. And with that, I'll turn it back over to Marilyn.
Great. Well, thanks, Peter and Steffi. So we have some great questions, and I will read them out. And if I could just ask the two of you to remember to unmute yourself when you're ready to answer a question. So, does HOMER account for negative impacts of the start-stop cycling of the diesel gen sets?
No, it does not. We've talked to a lot of diesel people about that, and we've never gotten good data on what that number should be. So, the short answer to that question is no. Okay. Next question. Actually, I can read these questions if you want. Whoa, except it goes back the wrong way. Someone asked about microgrids that are connected to the grid some of the time, but not all of the time. And we consider that a grid connected. even though that doesn't mean it's always connected to the grid. And we have a variety of ways to model outages on the grid. The second part of that question had to do with preventing the battery from being charged by the grid. And that capability is in HOMER. It might be a little hidden. You have to go to the specific rate period, because we can restrict that in during peak periods and allow you to do during off-peak periods, or you can restrict it all the time. So that's a parameter that needs to be set based on the rate period. So then the next one is not really a HOMER question, but I'll take it anyway. Is there a reliable model to convert battery bank terminal voltage to stated charge? Because most monitoring systems would measure battery voltage in real time and not state of charge of the battery bank. Well, that's a very legitimate point. There are some monitoring systems that count amp hours going in and out of the battery, amp hour counting algorithms that would be more accurate. And there's data you can usually get from the battery converting converting voltage to stated charge. It's also a function of whether that changes dramatically depending on whether power is going in and out of the battery. So it's a very legitimate question. It's not really a HOMER question, and there's lots of ways to do it, but there's obviously it's never a perfect science there. The same person asked a question here: for multiple DG systems, does HOMER allow for cost and losses of master control unit during the control in real time? Well, we definitely allow for the cost of the controller. And it's a very legitimate point that a real-time controller is going to be operating differently than a simulation engine operating in defined time steps. And every controller is different. The industry is coming out with sort of new control hardware and software all the time. I don't really have a good way to estimate what the difference is between a real-time controller, but over time we'll have more and more information about that. When will generator order capability be added to HOMER grid? And there was another question similar to that. We don't have any immediate plans to do that. We have a regular roadmap, and we've been coming out with quarterly releases with new features every quarter. So that belongs on the roadmap, and we should probably query our users about that. The question was, another similar question later was about redundancy, that a lot of microgrid operators or designers will want redundancy. And if it's truly just about redundancy, then you've got two generators, but really only one's going to be operating at any one time. HOMER can model that as a single generator. You can double the capital cost because you have two, and double the lifetime, is the way I would model a truly redundant system like that. But a microgrid where you really care about, with multiple generators, where you really care about the dispatch order, is quite a large microgrid. We're thinking about for us. It's not something we're planning to do in the next couple of months, though. I will say that. Forecasting errors. Well, the way to think about this is that we can bracket it. Here's what your results would be without forecasting errors, and then our other dispatch strategies are, here's what your outputs would be if you weren't forecasting at all, and so that brackets it. It's an interesting question, adding that kind of forecasting error to it, and we actually did play with that quite a while ago, and all we did was confuse users, to be honest, so we stopped trying to do that. But it is a very interesting question. The next question here is Isn't the predictive algorithm something the users can themselves employ for microgrid based on historical weather data, et cetera? Oh, sure. I'm not sure if you're asking about in HOMER or in a real system that's been built, but in a real system that's been built, if you want to get into manual control, you can do pretty much anything you want. And the next question was a really specific question about one of Steffi's graphs, and about the x-axis was 24 hours of the day, I'm pretty sure. It might have been more than one day though, right? And it's not clear which graph that was, but yes.
It's not useful now.
Yeah, yeah. Okay. Availability of only a single generator is a significant limitation on this. Oh, this is the one I was already referring to. It's quite a long question. So adding generator order to HOMER grid belongs on our roadmap. These webinars are great for getting feedback like that from our users. How can the dispatch strategy be explicitly controlled in HOMER grid? Well, HOMER grid's our newest software. We do have this MATLAB link to allow you, for HOMER Pro, to allow you to be, oh, can you all hear me? Okay, I just got a little message that my audio was lost, sorry. So we do have these two ways to create your own dispatch strategies for HOMER Pro. The simple one is the MATLAB link, but you need MATLAB for it. And the much more sophisticated, faster one is uses C++. Arby is going to be talking about that next month in much more detail. That currently isn't available for HOMER grid because it's such a new product. Again, it's on a roadmap, and getting questions like this sort of elevates it a little bit on our roadmap. When will cost escalation be built into grid the same as Pro?
Multi-year.
What's that?
Multi-year.
Multi-year, yeah. Steffi, that actually is on our roadmap for probably not the next release, but that's actually one of our higher priorities. So I'm going to guess early 2019, but don't hold me to that. But that is one of our priorities to do that. Regarding the predictive dispatch, is this control based on a forecast of generation resources only, or does it also forecast the loads? Yes, it looks at both. Absolutely. Thanks for the answer. The is based on like. Right. Well, the next one's not really a question, so I'm gonna skip over that. Can the attendees read these questions?
No.
Okay, so I
Read them clearly.
that was just somebody thanking me. So thank you for thanking me. But can you only limit battery charging from the grid based on peak load periods? What if the country has a flat grid purchase rate throughout? Oh, absolutely. I just said that as an example, but you can limit battery charging from the grid in whatever rate period you want, or all the time. And flat grid purchase rates are the easiest thing to model. So the answer to those questions are yes, that you can limit battery charging from the grid for whatever periods you want, including all the time. The advanced grid module in HOMER Pro. Somebody's asking about the capabilities of the advanced grid module in HOMER Pro. That's quite a long question. The one thing that HOMER Pro does, which we're adding to HOMER Grid in the next month or two, but that HOMER Grid doesn't currently do, is if you have a really unreliable grid with lots of outages, maybe weekly outages, sort of a developing country kind of scenario, HOMER Grid currently can handle what we've been calling resilience, but it's really the extraordinary outage, the hurricane that brings down the system for a week or two, and it doesn't necessarily happen every year. But if you have regular outages, frequent outages, that's where HOMER Pro has a capability that we're currently right now putting into HOMER Grid, but it's not in the public version. But HOMER Pro, the advanced grid allows you to have multiple rate periods, it allows you to have demand charges, it allows you to use real-time rates, it allows you to look at comparing grid extension to a microgrid, an off-grid system. And you, am I missing anything? What else? What did I miss? Anything else? Did I cover most of it?
Main difference is the algorithm in HOMER grid.
Right. Well, the dispatch algorithm is really different. Right. Exactly. Here's a question that just says multi-year. That's not really a question, so I'll move on. Are there general designing rules which distributed best fits? Well, there's rules of thumb, but I always get nervous about rules of thumb because that's one of the reasons we created the software, is we realized the rules of thumb actually aren't really good enough most of the time. And I mentioned, so having said that, I will give you a generalization that load following tends to be better for higher systems with higher renewable penetration, and cycle charging tends to be better for systems with lower renewable penetration. But that's just a generalization, and it's definitely not always true. So that's why you have a software. You run both and see which one is better, and you see under which conditions which one is better. What I can say, though, is the generator order is clearly preferable if you have, more than 3 generators, just for runtime reasons, and just confuse. It's just a lot easier to work with, but and more consistent with the way those systems operate. So that's a generalization that I'm very comfortable with. Let's see, we all do many activities to lower the CO2 emissions, slow down the climate change, but it seems that we are not successful. Do you think that this isn't really a HOMER question, but do you think that all the institutions should concentrate more on this issue, and what is your strategy in climate change as HOMER? I don't know if that's it, got cut off there, so that's all I can see for the question, and it's not really a HOMER question, but obviously one of the big motivations here is to reduce emissions. It's one of several. Reduce costs is another one. Reduce fuel consumption for economic reasons. Increase reliability. There's lots of reasons to do distributed generation and microgrids, but reducing CO2 emissions is one of the most important ones, and that's part of the motivation we're here. So our mission as a company is to provide this tool to help people all over the world reduce their emissions, and we've always thought the most effective way that we can help is to provide this tool, because to really have an impact on climate change, we need thousands, maybe millions of these microgrids out there, which means we need hundreds or thousands of people who know how to design them and understand how they work and what makes sense, what doesn't make sense, etc. So creating this software and making it widely available, that's our mission, and that's the greatest contribution we can imagine that we can provide to reducing climate change. Okay, there's a couple more questions here, but we're running out of time. I'm going to skim them. So the last one's a good one. Can you change the battery life calculations by cycles instead of throughput? We have an advanced storage module. If you go into our library and look for a battery with ASM label attached to it, you can copy it and edit it, and it gives you an enormous amount of flexibility about changing the parameters, including the lifetime calculations. So we should have a whole seminar. I think we are going to have a webinar, but not next month, sometime in the future, just on our advanced storage module, which is quite sophisticated. Oh, one more came in, but we're running out of time. Yeah.
So thanks, Peter. I know I just wanted to end it because we've kind of filled our time. But so our goal for today is to present you just an overview of these dispatch choices that you have in HOMER. There's a lot here, And so I just want to spend 1 minute encouraging you to partner with us. I want to present 3 educational and support opportunities that we offer. The first is our training programs and our premium support system. You know, online, at your place, whatever you need, we can do your modeling for you, check your results to make sure they were done correctly. The other is this training, this educational webinar series that we're doing. So we've talked about RB next month. Our follow-up email to this will have a link to register for that. So for those of you who are in the research mode, how do you create your own control systems in HOMER and play with that? And then the controller API actually lets you release those in a public version or in your organization if you want to. The final one is that in just a few weeks in San Diego, California, we're holding our International Microgrid Conference, which has a full day in-person HOMER training with both advanced and beginning and advanced tracks. So that's where you could get all of your questions about dispatch or anything else answered and work directly with our engineers. So thank you again for attending. If you did not get your question answered, please send it in through your sales rep or our support desk, and we hope to see you in October in San Diego or at our next webinar. Thank you.